Hello ladies and gentlemen, this is Norris Salam for Schrödinger. In this example, we are going to demonstrate how to combine Canvas binary fingerprints with kernel-based partial least squares, or KPLS for short, to build a regression model for predicting activity. Now, the incorporation of Canvas fingerprints will allow us to map the atomic contributions each molecule makes towards activity. In other words, to visualize potency and to subsequently make rational decisions for further lead optimization. So here we have in our Canvas project a dataset of about 70 CDK2 inhibitors, which is a high enough number to generate a statistically valid model. You'll notice we already have a set of properties listed, in particular PIC50 in the first column. PIC50 is our activity data and will ultimately be the Y variable when we go to build the KPLS model. But before we can get to that point, we must first generate binary fingerprints. Now, KPLS will work fine with ordinary properties, but if you want to visualize the model onto the structures, which is the major strength of the method, we need to use fingerprints. So we'll head on up to Applications, Binary Fingerprints, then choose your fingerprint. In this case, we'll go with dendritic, and then Create. It's a very fast calculation, so one CPU is just fine in this example. Once the job is done, click OK and head on over to the project view to right-click and incorporate the fingerprint job. Now that we have fingerprints generated for all structures, we can proceed with the actual kernel-based PLS calculation. Head on up to Applications, then Kernel-Based PLS Regression. We'll select our Y variable as PIC50. The properties to choose will be the dendritic fingerprints generated in the previous step. Now, just to emphasize a key difference to other methods, in that while you can certainly mix fingerprints with ordinary properties for model building, in order to visualize the model onto the structures, you have to pick pure fingerprints. Select the maximum number of factors, keeping in mind not to choose too many to cause overfitting. The kernel non-linearity of 0.05 is a good default, so that can remain unchanged. For the training set, we'll choose a random 75%, but we'll make sure it's reproducible, so we'll remember the seed as 1, 2, 3, 4, 5. And click Apply. When ready, click Build Model. After the model has been built, we can view the statistics for the training and test set for the various factors. 5 factors seems fairly good in this example, with a reasonable Q-squared of 0.728, so let's select it and quickly take a look at the scatter plot. Red dots are the training set and blue correspond to the test set. I'd say it looks fairly predictive, although perhaps a minor outlier over here. Now, while it is all fine and good to generate predictive models, the real power of kernel-based PLS regression is being able to map the models onto each structure. So let's finally do that. We'll head back and click Visualize Model to open the Model Visualization window with the table of structures. We can see here the atomic contributions, or the sensitivity of the predictions to the presence of each atom. We chose a color ramp that is colorblind friendly, so the default coloring scheme is red to represent a tendency to increase predicted activity, while blue represents the presence of that atom decreasing the predicted activity. Now, I'm not colorblind, so I personally like to change the default to red and green. So let me just show you how to do that by clicking Min and then Red, and then clicking Max and then Green. Okay, so now in my example, green represents good or increases predicted activity, and red is now bad or decreases predicted activity. In addition to looking at all the structures at once, you have the ability to drill down for details about what is going on with an individual structure. To do so, double-click one of the structures. In this example, if we hover over, say, this nitrogen red, we see a tooltip displaying the contribution as negative 0.066, which is unfavorable. Let's contrast this to one of the nitrogens in green, where we see the contribution as positive 0.235, indicating this particular nitrogen feature has a significant contribution towards predicted activity. Now, behind the scenes, we are dealing with fingerprints, and a given bit in a fingerprint represents a fragment in the structure. So while we are breaking this up into the atoms that are in each fragment, sometimes it's the fragment itself that is important and not just the atom. So if you want to know what fragment amongst your dataset a particular atom is found in, then you can double-click on it, and it will open up another table called Fragment Contributions. In this example, there are 4 fragments that contain this particular nitrogen. A really powerful feature you can leverage from here is to explore what would happen if you made changes to any structure. So for this example, can we improve on achieving a higher predicted PIC50 than 8.556? To do so, click Edit to bring up the 2D sketcher. In this example, we shall remove the methyl as that appeared to have a negative contribution to the activity, and we shall see if removing it improves the overall predicted activity. And yes, we find that we have improved the activity up to a PIC50 of 9.657, so clearly a good modification. From here, we can save the new structure to the project table or click Reset and try another modification. Now keep in mind of the limitations when designing and optimizing structures this way, in particular when attempting to improve the already most active compound, only because by that stage you may already be extrapolating beyond the limits of the model. A good recommendation would be to instead focus on comparing different compounds, taking the best existing feature from one and adding it to the other, or in the case that we just did, remove an existing feature that was shown to decrease activity. This of course is made easy here because we identify those good and bad features with the help of the coloring map. So in summary, if your end goal is to build a predictive model that is sophisticated enough to allow you to visualize the atomic contributions towards activity and then make informed lead optimization decisions and test new hypotheses quickly, then I strongly recommend you try out Kernel-Based PLS with fingerprints from within Canvas. For more information on Kernel-Based PLS regression, please refer to the Canvas user manual or contact help@schrodinger.com. If you are new to the Schrodinger suite and would like to gain access to KPLS and many other useful cheminformatic features from Canvas, please contact info@schrodinger.com.